Hey Yahoos, sorry I can't be here with you today. I'm out with the 10th grade ski trip, and it's not quite as much fun as hanging out with you. Anyway, last time we were together, we were looking at balancing the chemical equation for hexane, and looking at the Lewis diagram, and we solved all the way through making and breaking the bonds. We're going to work on the back page today. We're going to look at moles, and then we'll have you work on a problem on your own and then study up for the quiz tomorrow. That is just on the basics of making, breaking bonds. We'll give you the tables for those, and we'll give you Lewis diagrams. Cool. All right, so here we go. If you didn't quite get it, we were working on this front part of the worksheet, the hexane worksheet last time we met, and we ended up with this figure, negative 7,691 kilojoules per mole. We'll talk about this kilojoules per mole. It's negative because the energy is supposed to be going into the bond. So if it's negative, it's going the opposite way. It's coming out of the bond. So this is exothermic. We calculated that we broke up the bonds, and it took 24,000 kilojoules to break up the bonds, and you got 32,000 kilojoules out. Make sure you can get those calculations. My calculations are up on the VLE for you to see if you need the play-by-play. I'm going to do the back with you now, so let's roll. We talked about specific heat, and we looked at this equation yesterday. And so from here, you can calculate how much energy experimentally should come out of this. So this first part is theoretically how much energy should come out, and this piece is experimentally. So as you plugged these pieces in, you said 200 grams times, well, let's get rid of that, the grams, times C, which is this piece, so 4.18. Oop, missed my one. Writing with the mouse, not my forte. And change in temperature is 34. So you multiplied all these together, and we got something to the effect of 28,424 joules. If you look at this, the units for these, they'll cancel out, and you'll just be left with joules. It's an interesting calculation, but you don't necessarily need to know that. You should know that since it's energy, since this is the energy required, the energy should be in joules. Great. So this is how much energy comes out when you raise, let's see, this much water, this many degrees. This is how much energy, it needs to go into warming that up. Great. So, or how much energy it takes to warm that up. We use 4.18 because we're using water, and that's the specific heat of water. How much it warms up per how much energy goes in. So now we're going to use that for part C, and many of you got this done already, but let's try it out. So since we're trying to calculate the energy per gram in hexane. Well, here we know how much energy goes out, and here's how many grams of hexane we burned. Right? When we were back here, we're talking about in the lab, we're going to burn some of this hexane. We're going to warm this water up. And to figure out how much hexane we burned, you can put it on a scale and weigh it before we do the experiment, and then weigh it after, and we can see the change in mass, the change in grams. So we can figure out how much hexane we burned, and therefore how much energy we got out. And then back here, we can figure out how much energy per gram. Well, okay, so here's how much energy we got out in our pseudo experiment. We got 28,424 joules, and it was by burning 4.2 grams of hexane, so over 4.2 grams of hexane. And so if we calculate this, just divide, I got 6,767, and that's in joules per gram, right? So this is joules per gram. Fine, great. So we're going to take that number and roll with it. All right. So moved on. Before you get to the next piece, which is this, this section 4 talks about enthalpy and efficiency and this sort of unit, kilojoules per mole and joules per gram. Yeah, they're different ways of discussing energy, and we want to be able to convert back and forth between them. And so far, we haven't looked at what a mole is. So we're going to look at a mole so it helps you understand how to convert them. The conversion isn't incredibly necessary, but you should know where it comes from. So here we go. A dozen. The word dozen means the number 12. So generally, we think of a dozen eggs because there's 12 eggs in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh man, there's not a dozen in there. 12. There we go. 11, 12. Usually a dozen means 12. I can't believe there weren't actually 12 in there. So if you have a dozen eggs, it means you have 12 eggs. And if you have a dozen red roses, these, I did count, you should have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's a dozen red roses. Fine. You can have a dozen ducks, right? There's a dozen ducks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 ducks, right? So that's a dozen ducks. So 12 just means, a dozen just means 12. And likewise, you can have a dozen hexane molecules, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a dozen hexane molecules. Fine. Likewise, you can have a quartet. A quartet we generally think of as 4 stringed instruments playing together. So here's a quartet of musicians. But it just means 4 of something, right? So you can have a quartet of dorks. There, 1, 2, 3, 4. A quartet of dorks. You can have a quartet of ducks. 1, 2, 3, 4. Ooh, also musicians, right? You can have a quartet of hexane molecules. 1, 2, 3, 4. The word quartet means a certain number of whatever you're talking about. Okay, let's move to moles. Okay, a mole is just like a dozen, just like a quartet. It means a certain number. So it means a really big number, 6.02 times 10 to the 25th. And you'll get deeper into that in chemistry about where that came from. But for now, what we'd like you to know is that a mole is just a really big number that is sort of like a dozen. It's sort of a group. And it's not very useful for things like ducks. That's way too many ducks to count. In fact, if you were talking about like rice, they're tiny, tiny, tiny grains of rice, it still would fill up mountains of rice, right? Just because it would be 6.02 times 10 to the 25th grains of rice, right? If you had a mole of moles, that's a mole. There's a great website that has a discussion about a mole of moles. It's up on the VLE. You can click on the link. But a mole of these little moles, which are like this big, would fill up higher than Everest, right? It's just a really big number. And you can have a mole of anything. You can have a mole of moles. You can have a mole of grains of rice. And also, you could have a mole of hexane molecules, right? Those are the same hexane molecules we've been looking at here, right? Hexane molecules. But instead of having 12 or 4, instead of having a dozen or a quartet, we have a mole of them. We have many of them. We have this many of them. I almost pointed with my hand, but you can't see me, can you? Right? So we have a mole of moles. Sorry, a mole of hexane molecules, right? We have 6.02 times 10 to the 25th hexane molecules. And that's called a mole. Great, fine. Okay, let's try to apply that. Okay, so in section 4, we're trying to convert kilojoules per mole to joules per gram so we can compare them. That's because back in here, we figured out that the theoretical energy amount that we should get out is 7,000 kilojoules per every mole of hexane, right? So if you have 1 mole of these, it really means you have 6.02 times 10 to the 25th of them. And when you have that many of these hexane molecules and combust them, you'll get that much energy out. So let's bring it back. What's neat is that you can look at the periodic table and look at how much all of these weigh and figure out how many grams hexane should weigh per mole. So we can figure out that hexane weighs 86 grams for every mole. So if you counted all of these up, where is it? If you counted all these up, let me move my face, what we didn't have hiding back here, was that a whole mole of them would only weigh 86 grams, yeah? Which isn't very much, even though you have a lot of molecules, because they're really small, yeah? So back here, we figured out that from our initial calculation on here, that we had 7,691 kilojoules per every 1 mole of hexane burned, right, per dozen. We want to change that to joules per mole with our stoichiometry that you learned in math class with me, right? So first let's change this kilojoules to joules. If you remember how to do that, you can say, all right, well, every 1 kilojoule is 1,000 joules. Right? Kilo is the prefix. We put the kilojoules on the bottom because the kilojoules and the kilojoules will cancel. We'll multiply everything on top, and you'll end up getting 7, 6, 9, 1, and 3 zeros joules over multiply the bottom. But now we've got joules per mole, per 1 mole, right? But don't stop there, right? I'm going to get rid of this, and I'm going to keep going with my stoichiometry, my dimensional analysis. So let's remove that and keep going with my purple. So I don't want moles. I want grams. And I know that in every 1 mole of hexane, there's 86 grams. Every mole weighs 86 grams, 86.18. Now we're in business because we can say, hey, moles on the bottom cancels out with moles on the top, and we'll be left with joules per gram just like we're interested in up here if I hadn't scribbled it all out. There it is. So let's do the calculations. Just going to multiply everything on top and everything on bottom and then divide. So when you multiply everything on top and multiply everything on bottom and divide, I got 44621, 44,621 joules per gram. Why we're looking for that unit of measure is because back here, that's what we can do experimentally in the lab. When we find all of this, when we look at the mass and the temperature change and the specific heat, our heat that comes out is either in joules or kilojoules, but we figure out per gram of hexane because we can weigh the grams. So this is this is experimentally what came out in joules per gram. So this is what came out theoretically in joules per gram. Yeah, this is equivalent to the 7,691 kilojoules per mole. It's just in the same unit as what we're looking for as joules per gram, right? So it's the same thing. So now we're going to look at the two efficiencies. So we want to look at how efficient did we measure it to be, how much energy was transferred that we measured, versus how much did we think was going to go on. So let's try that out. Experimentally, we found that this was our experimental value. So 676, let me see if I can copy that and paste it over here. So this was our experimental value in joules per gram, and let's divide by the theoretical value that we just found, which is 44621 joules per gram times 100. This is sort of saying, I think this should come out theoretically by what we counted all the bonds. This is the number that we think the energy should be coming out per gram. And this is, hey, we measured this much energy change by measuring the temperature change of the water, right? So those are the two pieces. Oops. And when you multiply those, I got like around 15%, right? So the setup that we're going to use, this, a Bunsen or an alcohol burner warming up some water, the chemical energy in the bonds in here, transferring that from here to actually the molecules of water bouncing around faster in here, that transfer is only 15% efficient. Why might that be, right? Think about what might happen there. That's sort of the basis of the pre-lab. And I'm sure you can guess a few of those off the top of your head. Great. So I hope you can follow through that and kind of figure it out with me. I'd like you to be able to do this concept without too much trouble. So I'd like you to try that in this section 5. Use ethane. It's the same thing as hexane, except you have less C's and H's. Find the theoretical amount of energy released by burning ethane in joules per mole. Oh, they just tell you. And then figure it out experimentally with this data and find the efficiency, right? Work on that through the end of class. Once you're done with that, or once class is over, even if you haven't gone through that, I'd like you only to, for tomorrow, look over your quiz. Yeah. So work on this guy till the end of class. Once you're done at home, look over your notes, or if you finish, look over your notes, and come in for the quiz tomorrow. It's up on the VLE. It's just breaking bonds and making bonds, and you'll be fine. And I will see you on Monday or Tuesday.